All right, moving on with U-substitution. This one's going to involve some trickier substitutions that are a little bit more difficult to see, and we're going to cover U-substitution with definite integrals and see how that works out as well. So let's look at this problem. Cosine over 1 plus sine squared. And when I see a fraction, my initial guess is to try to let u be the denominator. I like to look in the bottom, and I don't see any parentheses. I see an x, but nothing fancy inside the parentheses. So I'm going to see what happens if I let u equal 1 plus sine squared x. Well, if u is sine squared, the derivative of that, remember we have to find du, and when you find your du, don't get confused by the way the rest of the problem looks. So I'm actually going to hide the rest of that problem, and I'm going to find the derivative of 1 plus sine squared, which that's really the same thing as 1 plus quantity sine x squared. And if I do the derivative of that, 1 goes away. I would bring down the 2, and then I would have sine x to the first, and then times the derivative of the inside, which is cosine x, and then finally the dx. Now, once I find my du, I look back at my original problem and I try to find du. So I'm looking for 2 sine x cosine x dx. And I don't have that. I have a cosine x dx, and I could fix the 2. That's a constant. So I could add the 2, but the problem is there is no sine x. That's an issue. There's no sine x by itself. So this u actually fails, and I need to go back and try something else. And what we're actually going to pick for u on this one is sine x, and that's it. So we're going to let u be just sine x. And the reason I want to use sine x is because I'm looking in the numerator, and I see cosine, which I recognize. In the back of my mind, I see that, and I know that that is the derivative of sine x. And so when I recognize the derivative of sine x, I'm going to let u be sine x, and that way du, when I take the derivative of sine x, du is cosine x dx. And now we can actually move forward with our substitution integration. I do see my du in the numerator, cosine x, and the dx is actually part of the du, so I'll extend this to include the dx. All of that is my du. And then when I do my substitution, I take out the sine x and put a u in its place. So this is going to turn into the antiderivative of, and I'm going to take out the cosine x dx, and there's my du. And then the sine x is actually going to come out, and it's going to become u, but it's sine x squared. So it's going to be something over 1 plus u squared. All of that is my du, so I'll just put a 1 in the numerator to hold the place. So I take out cosine x dx, there's my du. Instead of 1 plus sine squared, it's 1 plus u squared. And hopefully you recognize that as the derivative of inverse tangent of u. Don't forget the plus c. So we've done the antiderivative. It actually ended up being arctan or inverse tan. And now finally we need to plug our sine x back in. So our final answer is going to be the inverse tangent of the sine of x. Dx, not dx, plus c. And there's how we're going to do that problem. So you can try different things for u, but know that it's vitally important that you find du in the problem. If you don't see the du, you have to start over and try a different u or a different integration technique. Let's give this one a shot. I have 1 over x, ln x. Again, I typically look in the denominator for my u. So if I tried u equals x ln x, when I do the derivative of that, that's a product rule. So du would be derivative of x is 1 times ln x plus, then be x times the derivative of ln x. And that derivative ends up being the ln of x plus 1 when you simplify. And I don't have ln x plus 1 anywhere. So again, my u choice failed on this problem. So I'm going to try something different. So let me erase that. That failed. I'm going to try something different. And what I see in this problem that I like is the ln x. Now, generally, we don't like ln x. You want to shy away from it, but this time we don't have a choice. I'm going to let u be ln x. And the reason I'm choosing u as ln x is because the derivative of ln x I know is 1 over x dx. And in order to do u substitution, you have to see du. And I do see a du. I have 1 over x dx right there. All of that is my du. And the ln x is my u. So I can actually do my substitution now. This is going to turn into the 1 over x dx. All of that comes out as my du. My numerator is kind of wrapped into the du, so I'll just stick the 1 on top. And ln x is coming out, which will be u. And so now I've cleaned it up to the antiderivative of 1 over u, which hopefully you recognize as the derivative of the natural log of u plus c. And then once you've done the antiderivative in terms of u, you take the whatever u was, which was ln x, and plug that back into your answer. So our answer is going to be the natural log of u, and u is the natural log of x. So we have the natural log of x plus c, and there's your answer. So remember, you absolutely have to see du in your problem. Let's try another one. Arc sine x over root 1 minus x squared. Now this one looks very intimidating and scary at first. Generally when I see a u substitution problem or a square root in an integral, I'm going to try letting u be what's inside the radical, but the problem is my du is going to be what? Negative 2x. That's the derivative of 1 minus x squared. And there's not a negative 2x anywhere in this. There's that arc sign, which is painfully ugly. So that fails. But I do know, and I hope that you know, in the back of my mind, that the derivative of arc sine x is 1 over root 1 minus x squared. And I see that in the problem. I have root 1 minus x squared in the bottom. And so I'm going to actually let my u, in this problem, my u is going to be in the numerator. So u is arc sine x, and the derivative of arc sine x is 1 over root 1 minus x squared dx. And like every other problem, you have to see du. Do I see, whoa, that was a bad rectangle. Do I see the root, or 1 over root 1 minus x squared? And I do. There's not a 1 written in the numerator. If it makes you feel better, you can put 1 there. But I do have 1 over root 1 minus x squared dx in the problem, and my arc sine x is going to come out as my u. So there's my u, the over root 1 minus x squared dx is my du, and then this is going to turn into the antiderivative of arc sine x comes out, that's u. Everything else is the du, and so it cleans up to simply the antiderivative of u du, which is u squared over 2 plus some constant. And then finally we plug our u back in. So my final answer is going to be the arc sine of x all squared all over 2 plus c. You have to find that du. So find the u and the du, then make the appropriate substitution. Let's see. This one creates a new dilemma. For this problem, I clearly see an inside of 1 plus x. So if I let u equal 1 plus x, the derivative of 1 plus x, and remember, don't look at the integral while you're doing the derivative. When we find the du, we completely ignore, where's my stinking curtain? There it is. We completely ignore the integral, and the derivative of 1 plus x is simply 1 dx, or just dx. So du is dx. Now I look back at my problem and I think about the substitution. Well, I do clearly see my dx. Dx is my du. So I can take dx out and plug in du. I can take out the 1 plus x. 1 plus x, that's my u. Right? But then we have a problem because there is still another x sitting here in the problem that we haven't accounted for. When you do the substitution, you have to substitute everything out. You can't leave some u's and some x's. So I've got to find out what I can do with this x, or we have to try a different approach. I do suppose if you wanted, you could completely multiply this out. You could do u plus x, 1 plus x times 1 plus x times 1 plus x times 1 plus x times 1 plus x, that's to the fifth power, and expand that out to the fifth power, but that'd be a pain in the butt. Not hard, just incredibly lengthy and troublesome. So I'm going to try to make this work. And what we're going to do here, I'll actually go through and do my initial substitution. I'm taking out the 1 plus x, and I'm going to plug in u to the fifth, and then I'm going to take out the dx and plug in du. So I'll plug in the dx, or the du for the dx. Now the problem is I still have this x right here that I need to account for. There's still an x in the problem, and you cannot have x's and u's, as I said earlier. Well, remember we're doing substitution here, and I know we're in calculus mode and we're thinking calculus, but the substitution itself is actually an algebra operation. All we're doing is taking out the 1 plus x and plugging a u in its place because they're equal to each other. I'm taking out the dx and I'm plugging in du because they're equal to each other. It's the same substitution you did in algebra. Well, what I'm going to do to tackle my x, since I see that u equals 1 plus x, I can take this equation right here. I'm going to get rid of that box. I can take that equation and I can actually solve that for x. If I subtract 1 from both sides, I get x to equal u minus 1. If u is equal to 1 plus x, that means x equals u minus 1, and I can actually take that and I can plug this in for the x right there. So now my integral is going to turn into the antiderivative of u minus 1, that's going in the place of the x, times u to the fifth du. And I now have everything in terms of u, and I can go on with the antiderivative. For this problem, it's a product, but I can easily distribute that u to the fifth. So it's going to turn this into u to the sixth minus u to the fifth. And now we have a nice cute power rule. U to the seventh over 7 minus, add 1 to the old exponent, u to the sixth over 6 plus some constant. And then our last step, remember we have to plug our x's back in for u. U is equal to 1 plus x, so my final answer is 1 plus x to the 7th over 7 minus 1 plus x to the 6th over 6 plus c. So there is our answer. Let's try another one along the same lines. I'm going to let, in this problem, u is going to be x minus 3. It's on the inside of the radical, so that's where my eyes are drawn. The derivative of that, the derivative of x is 1. The derivative of negative 3 is 0, so we're left with 1 dx, and we have the same situation. Here's my u. Dx is my du. But again, we have an x that's not accounted for. I've got to do something with this x right here. And in order to substitute for that x, I'm simply going to take this equation. If u is equal to x minus 3, that means x is going to equal u plus 3, and that's going to go in the place of the x. So we'll go through with substitution. X comes out, that becomes u plus 3. The square root remains, but under the square root, instead of x minus 3, I'm going to put the u, and then the dx comes out and becomes du, and now we're back to kind of where we were in the last problem. This is a little bit uglier because of the square root, but the concept or the execution of this integral is going to be about the same. I'm going to change the square root of u to the 1/2, and then like that last problem, I'm going to distribute the u to the 1/2. Just remember that you add the exponents. U to the first plus 1/2 is going to be u to the 3/2 plus, and that's 3 times u to the 1/2. And then we'll do the power rule. 3/2 plus 1 is 5/2. You divide by 5/2. It's the same as multiplying by 2/5 plus 3 times, add 1 to that one, u to the 3/2 divided by 3/2, which is times 2/3, plus c. And I'm going to go crazy here. This is unlike me, but 3 times 2/3, those 3's cancel. And at the same time, I'm going to plug my x minus 3 back in for u. and then we'll have 2x minus 3 to the 3/2. Okay, so there's our final answer for this one. There's really no fancy name for this that's endorsed by the Math League of America. I've heard some teachers refer to this type of problem where you kind of have to substitute something weird back in for x. I've heard this called an ugly U problem. I've called it a double substitution. Double substitution. Or I guess you could call it dub sub. That's kind of cool sounding. Dub sub. Which I misspelled the dub part, but hey, that's cool. Anyway, so sometimes you have to do a little bit of algebraic manipulation in order to get the substitution to work. There are 2 more problems I wanted to look at, and these are problems from the definite integral world. We haven't done any definite integrals with U-substitution. I'm going to show you 2 ways to solve this one. The first one, we're simply going to ignore, we're going to pretend that those aren't there. We're going to ignore the limits of integration, and we will solve this integral like we normally would. We're going to find the antiderivative as usual. So I'll let u be 3 plus x squared. That's on the inside. Du is going to be 2x dx, right? Well, I have the x dx. I'm just missing the 2. And remember, if you're missing a constant, that's no problem. I can throw a 2 in here as long as I offset it with the 1/2. So now I'm going to go through my substitution. That's going to be 1/2 the antiderivative. 2x dx comes out as a du. 3 plus x squared is my u, and that's to the 4th power. And then I'll do the antiderivative, make that u to the 5th over 5. Now what you have to be careful is you cannot plug in 0 and 1 because those are values of x. They are not values of u. So before I plug in my limits of integration, I have to turn this back into a function in terms of x. So 3 plus x squared. Whoops. So yeah, 3 plus x squared all to the 5th over 5. And now we can evaluate from 0 to 1. I'm going to leave the 1/2 out. And when I plug in 1, you get 3 plus 1 squared is 4 to the 5th over 5. Minus, now sometimes when you plug in 0 everything goes away, but that doesn't always happen. When I plug in 0 here, 3 plus 0 is 3 to the 5th over 5, and that is our final answer. Good? Good? That is our final answer. Now I'm going to show you a second way we can solve this problem. And what we're going to do is the only different part is going to occur after you find the initial antiderivative. So let's look at, whoa, that's huge! Let's look at this problem again up to this point. What I could do, once I find the antiderivative in terms of u, since I know that u equals 3 plus x squared, what I can actually do is change the limits of integration to be values of u. I know that my lower limit is x equals 0, and if x equals 0, then u is going to equal 3 plus 0 squared, which is 3. So my u limit of integration would be 3. And if x is equal to 1, which is my original upper limit of integration, I could do 3 plus 1 squared, which is 4. And now I can evaluate this integral in terms of u from 3 to 4. And you'll see we end up with the same thing. So that'll be 1/2 times, I'll plug in 4 to the 5th over 5, minus, and then I'll plug in 3 to the 5th over 5. And that's our answer. I personally like to change the limits of integration. That's my preferred method. And I can cleverly word multiple choice questions where you have to know how to do this. So don't just blow this off and say, well, I'll just plug my x's back in, because that's not always an option. One more problem. I know I'm pushing 20 minutes, but one more problem. 0 to the power of 4 of this problem. I'm not going to toy with this one too long. Sometimes I'll intentionally make mistakes. But I see secant squared, which I recognize as the derivative of tangent. So I'm going to let my u be tangent x. And if u is tangent x, then du is going to be secant squared x. And this turns into quite a nice antiderivative because I've got my dx for du. Here's my du right here. and then my u is in the denominator. And so I'll change this integral into the antiderivative of 1 over u du, which is nice. I'm also going to change my limits of integration using this right here. If u is equal to tangent x, then if x is equal to 0, that means u is going to equal the tangent of 0, which is 0. So that one actually didn't change. If x is equal to pi over 4, which is my upper limit of integration, then u is going to equal the tangent of pi over 4, which is 1. And that's very nice. I like that. Now when I work out this integral, the antiderivative of 1 over u is the ln of u. Did I really create a bad problem? Stinky fizzletooth. Whoops. Okay, bad problem, because now I'm going to evaluate this. How did I do this? You can't divide by 0. I put a vertical asymptote in the original problem. I'm such a dumbhead. Okay. Well, you know what? I'm going to go ahead and finish this problem as it is. This would be the ln of 1, which is 0, minus the ln of 0, which is undefined. Wow, I can't believe I did this, and I'm 21 minutes in, so I'm not about to start recording all over again. This is actually what's referred to as an improper integral. Boo, that doesn't work. And improper integrals are strictly an AP Cal BC concept. And so we're not going to worry about finishing this up because it involves limits and some other weird techniques that we're not going to worry about in AB. So anyway, so this is, as far as the substitution and changing the limits of integration, everything was good. It just kind of blew up in the end. We won't work with improper integrals. I don't feel like messing with this right now, but there we go. Yay.